This video is on mass spectroscopy, otherwise known as mass spec. So we'll start by defining what that is. So mass spec is a graphical way to show the number of isotopes, their masses, and their percent abundances for a particular element. So we've learned at this point that all atoms on the, or elements, on the periodic table have numerous isotopes that exist for each one. We also know that the mass on the periodic table is a weighted average of all of the masses of the isotopes that exist, taking their abundance into consideration. So that's all stuff that we've been learning in this current chapter. So now what we're going to talk about is this idea of mass spec or mass spectroscopy, and how that it's really just what we've learned already, but applying it to a graph. So a mass spec graph will look like these examples that are shown on your note page. And so there's several different examples that we'll talk about, but they are always a graph of mass on your x-axis and either percent abundance, which is based on a scale from 0 to 100, because all percentages are based on 100%, or what we call relative abundance, going from 0 to 1, which is just percent abundance but as a decimal. So percentage divided by 100. Okay, so we can see both. It'll either say percent abundance or relative abundance, and the scale will be according to whether it's not a percentage or a relative abundance. On every mass spec graph, we'll see bars, and it's the number of bars that tell you how many isotopes the element has. So in this first example that you're seeing, we see that it's a percent abundance graph, and this is chlorine, and chlorine has two isotopes, chlorine with a mass of 35 and chlorine with a mass of 37. We can clearly see from the graph that chlorine with a mass of 35 is much more abundant than chlorine with a mass of 37, and they're on somewhere around 75% abundant for 35 and about 25% abundant for 37, which would come into play if we were doing a mass calculation. But that's just what the graph might look like. So moving forward from there, we're going to see an actual practice problem that gives us a mass spec, and it asks us what's the average atomic mass for this element, and then to identify the element. So the first thing we have to understand is that this is actually giving us relative abundances. Notice it's 0.1, 0.2, 0.3, and so forth. So they're already not in percentage form, which is what we would want for a weighted average calculation, so we don't have to divide them by 100. We also need to keep in mind that whoever this mystery element is, it contains 5 isotopes. I know that because there are 5 bars, and we want to use the graph to attempt to calculate the average atomic mass. So what we would do that by taking the mass of the first element, which is 76, and multiplying it by its abundance, and it's just under 0.1, so I'm going to go with probably 0.09. Meaning that's 9% abundant. To that, I'm going to add my second isotope, which is 77. And I think that's, a little bit less. I'm going to go with 0.07, so about 7% abundant. Isotope with a mass of 78. Somewhere in the neighborhood of, let's see, maybe 24% abundant, plus there is no 79, so be careful. Isotope with a mass of 80, which is pretty dead on at 50% abundant, or 0.5. And then no 81, but 82 with a mass. I think that mass is actually in between this one and this one, so I'm going to go with 8%, or 0.08. So this is a little bit of a lesson in estimation, but also in doing a percent weighted average calculation from data on a graph. And if we add all these together, I have to do it because I hadn't done it before. We will get the weighted average, or the average atomic mass of this mystery element. And I'm getting somewhere in the neighborhood of 77.5 atomic mass units. And if we go to our periodic table and we look for whose mass is closest to 77.5. It's not exact, but we see that SE is the closest one on our periodic table, and so we're going to identify our mystery element as that. So that's how to do a weighted average calculation from a mass spectroscopy graph. And so from here, I want to look at a couple similar yet different problems on what could you be asked from a mass spec graph. And so there's kind of a list, and the list is that there's basically 3 types of mass spec questions you could be asked. You could be asked to estimate the average atomic mass from the graph. It could be a fictitious element, meaning it might not even match somebody on the table because maybe it's a fake element. You could be asked to identify the element from the mass spec, kind of like what we just did. You could also be asked to identify a particular isotope from the mass spec, and we will see an example of that in a second. So the 3 examples of what you could expect to see. The first one, determine or show the calculation for chlorine's atomic mass. So if this was the question you were being asked, you would say, okay, I can calculate the average atomic mass by taking the mass of the first isotope, which is 35, and multiplying by its abundance. Now this is percent abundance, so we'll have to divide by 100. I think that's about 75%, and so that would be 0.75. Add to that the second isotope, who has a mass of 37, and that's about 25% abundant, or 0.25. So if you do this calculation, you end up with the fact that chlorine has an average atomic mass of 35.5 AMU. And if we look on the periodic table, it is very close. Keeping in mind a couple of things, we know that 35 is more abundant than 37, and so this mass should be closer to 35 than it is to 37. It is, and so this is one of those situations where we can say, hey, I think our calculation or our answer makes sense. The second type we could see is which element's mass spec is shown on the graph below. So sometimes a calculation is required and sometimes it's not. So in this case, I would say we can probably just estimate this. I know the average atomic mass is going to be somewhere between 39 and 41. And knowing that somewhere in the neighborhood of 90% of this element has a mass of 39, it means my average atomic mass is going to be very close to 39, but a smidge higher because of these two's contribution to that. So I would say it's just slightly larger than 39. You're welcome to do the actual calculation if you want to. I would not. I would say you could definitely save yourself time and say that the only element on the periodic table who has a mass that's just slightly greater than 39 is potassium, who is the symbol K. And so that's how you could do that type of question. And then for the very last one, identify the element and the number of neutrons in the atoms represented by the peak at 74 AMU in this mass spec. So I'm going to approach this one slightly differently. I'm going to show you a little bit of a trick. If we look at this, you could really bog yourself down with the time it takes to do this calculation, although you could do it. We have the 5 isotopes, and we know their percent abundances, or we could estimate them from the graph. And so we could do this calculation like we did before, but we could also see that if I take the first 2 elements who have isotopes, have an abundance of 70, or mass 70 and 72, who have abundance of 20 and close to 30, that accounts for about 50% of all the isotopes of this element, meaning that all the rest of these would have to account for the other 50%. And this is something that you might not see other than the fact that I'm guiding you to look at it this way, which means that if that's the case, my mass must fall somewhere in the neighborhood of 72 to 73. And if we use our periodic table to determine who that is, the only one who makes sense is GE, who has a mass of 72.61, and that falls perfectly in between those 2 numbers. And then we have to answer our question, identify the element. It is GE, but then they ask us, to then account for the number of neutrons. And so in the peak, how do I get that to go away? There we go. In the peak at 74, well, 74 is here. And so my mass of 74, remember, is protons plus neutrons. If I subtract from that the protons in GE, which is 32, because that's GE's atomic number, then I get the fact that I should have 42 neutrons in the peak representing the mass of 74. And that's how you could do a problem that was that third situation about identifying a specific isotope from the graph.